Thank you very much. Can you hear me in the back? Okay. So, so today I will talk about something called grade restriction rule and its application to strong weak Calabi-Yau correspondence. And this talk is based on joint works with many works with David Ton, Manfred Herbst, David Page, Maurizio Romo, who is sitting here, and Richard Eager, Johanna Knapp. And also I'm very much inspired by the work by Walt Donovan and Ed Siegel and Nick Addington. So, so there's a class of 2D 2,2 supersymmetric gauge theories called gauge linear sigma models. And they provide explanation of or gave birth to some interesting correspondences called Calabi-Yau LandauGinzburg correspondence or McKay correspondence or Calabi-Yau correspondence. So let me show you some simple and typical examples. The first one is found by Edward Witten, and it has gauge group U1 and 6 fields, 6-dimensional matter representation, charge 1 field, 5 charge 1 fields, and 1 charge minus 5 field P, and with some superpotential specified by a quintic polynomial, a generic quintic polynomial. And this has, because it has U1, there is one parameter called Fi parameter and one parameter called theta parameter. And this parameter is very important. It specifies so-called the phases. For positive zeta phase, the theory, gauge theory, reduces to sigma model, whose target space is quintic Calabi-Yau threefold determined by this quintic polynomial f in CP4. For zeta negative, the gauge theory reduces to LandauGinzburg overfold of 5 variables x and superpotential f, modeled out by this gauge group Z5. So this is this picture shows that there's a one complex parameter family of QFTs, or more specifically CFTs, where in one limit it reduces to sigma model, and in the other limit it reduces to LandauGinzburg overfold. And there's some special singular point where there's a Coulomb branch in the gauge theory. So this is the typical example. And I will mention a consequence of this fact. And there are similar examples. A simpler example which shows McKay correspondence for the case when gauge group is U1 and this matter representation, and in one phase you have overfold, C2 mod Z2, and the other phase it's minimal resolution, Eguchi-Hanson space. And another example is the flop transition. So again, simple gauge group, simple representation. And this is, in both of the phases, it corresponds to resolved conifold, resolution of this conifold singularity or ordinary double point. And the two sides corresponds related by flop transition. And this is an example of Calabi-Yau correspondence. And in these models, the phases are weakly coupled in the sense that the gauge symmetry is completely broken or broken to a finite subgroup. And the classical analysis is enough to read off the low energy behavior of the gauge theory. But there are interesting models with strongly coupled phases where a continuous gauge symmetry remains unbroken, and you need a hard physics analysis to find the low energy behavior. So one example is called Rudland model, named after the picture found, named after a mathematician who found a picture, or maybe I should say Rudland and Van Straten model. Anyway, this has gauge group U2, and matter representation is this: 7 copies of determinant inverse representation and sum of 7 copies of the fundamental representations. And the fields are denoted by P's and X's, and with some specific superpotential. Where this bracket Xi, Xj is this symplectic pairing under which and for which U2 under which U2 under U2 it transforms as determinant. So this is gauge invariant combination. And this aijk is a generic coefficient, and I will write. It is convenient to write this superpotential in this way. So aijp is the antisymmetric 7 times 7 matrix, which depends on p linearly. So this is like a mass matrix for the x fields. Or alternatively, you can write it as p times x, akx. Akx is this the linear combinations of this symplectic invariant. So this theory U1 again has one Fi parameter, one theta parameter, and it has two phases, as in U1. And for zeta positive, the U2 is completely broken, so this is weakly coupled phase. On the other hand, for zeta negative, SU2 subgroup of U2 is completely unbroken, so this is the strongly coupled phase. So this requires hard physics analysis, and let me show you the essence. So for zeta negative phase, SU2 gauge can be regarded as SU2 gauge theory fibered over CP6 coordinatized by P field, and 7 fundamentals with mass matrix aijp. And for generic choice of this coefficient aijk, this 7 times 7 antisymmetric matrix can have rank 4 or 6 for non-zero p. And for rank 6 locus, there's only a single massless fundamental, and in that case, you can show that supersymmetry is broken, namely there's no zero energy state. So the low energy state wants to be away from this generic locus and focus on this rank 4 locus. In the rank 4 locus, there are 3 copies of massless fundamental representations. And you can also show that in the low energy limit, it flows to free theory of 3 composites. And using these facts, embedded into this gauge linear sigma model, you can show that the theory reduces in the infrared limit to again a sigma model whose target space is the rank 4 locus, which is also called Pfaffian variety. So again, in the end, it is a sigma model. So in the weakly coupled phase, it reduces the sigma model found just by classical analysis, zero locus of ak of x's inside Grassmannian G27. So it is a Calabi-Yau threefold, 7 equations in 10 manifold. And in the strongly coupled phase, as I said, this reduces sigma models to Pfaffian variety. And once again, this is a Calabi-Yau threefold. But these two Calabi-Yau threefolds are not even birationally equivalent, but they sit on the same moduli space, Fi theta parameter space. So this is an example of strong weak Calabi-Yau correspondence. And this particular example is also known as Pfaffian-Grassmannian correspondence. But there are other examples. This is a model called Hosono-Takagi model, named after Hosono-san and Takagi-san's work. So the gauge group is O2 times U1, modded out by Z2 subgroup. And it has this matter representation. So O2, so this first entry is the representation of O2. So C plus is one-dimensional representation, trivial representation. And C2 is the fundamental vector representation. And the second entry is the charge under this U1. And again, I call the fields P and X. And the superpotential is very similar to the Rotland model, where this parenthesis xi xj is the orthogonal invariant. And as in Rotland model, it is convenient to write the superpotential in this way. Sijp is symmetric 5 times 5 symmetric matrix, which is linear in P. So this is again the mass matrix for x's. And also, alternatively, you can also write it in terms of P times Sk of x. Sk of x is bilinear in x. So very similar to Rutland, in the zeta positive phase, the gauge group is completely broken, so it's a weakly coupled phase. In the zeta negative phase, O2 is completely unbroken, so this is strongly coupled phase. And you need a hard physics analysis of O2 gauge theory. And let me show you essence of this. So this phase is regarded as O2 gauge theory fibered over CP4 with coordinate P, with 5 fundamental fundamental represented matters, x's, with mass matrix Sijk. And for generic choice of quotient, this 5 times 5 symmetric matrix can have rank 3, 4, 5 for non-zero P. And for the rank 5 locus, there is no matter, so it's like a pure O2 Yang-Mills, and you can show that there is no zero energy state. So you want to be away from this generic locus. And on the rank 4 locus, you can show that there are 2 vacua, and rank 3 locus, there's a single vacuum. And so this YS is the rank 4 or less locus, and this has a 1 singularity along this curve of rank 3 locus. Okay, and with a finer analysis of in the neighborhood of this, you can also show that the theory, the model, the gauge linear sigma model, flows to sigma model to target space, which is a refined double club of YS. So which is, YS has this A1 singularity, but this is unfolding this A1 orbifold singularity near this locus. So this is again, again in the end, it is a nonlinear sigma model to the target space, which is a smooth manifold. And for zeta positive, it's weakly coupled by classical analysis. You can show that it reduces the sigma model, whose target space is this complete intersection of 5 hypersurfaces in CP4 times CP4 modulo the exchange of the 2 factors by this O2, and this is called ray congruence. And in the strongly coupled phase, as I said, this reduces to nonlinear sigma model, whose target space is this double branched ramified double cover of YS, rank 4 less locus, ramified over rank 3 locus. And both of them are Calabi-Yau threefold, and they are not birationally equivalent. And also in these 2 models, there are dual models found by something called Seiberg duality, or something 2D version of 4D Seiberg duality. And in this dual model, the role of strong and weakly coupled phases are exchanged. So the Rudder model, the dual model, has this gauge group. So U2 can be regarded as USP2 times U1 mod. U2 is SU2 times U1 mod plus minus 1 plus minus 1. Well, this is alternatively, this is also called USP2. So I use Seiberg duality for this USP2 gauge theory with 7 fundamentals, and then the gauge group turns into USP4 with 7 fundamentals. And also you need additional additional singlet, some additional field which is neutral under USP4. So this is the dual model, the gauge group of the dual model and the fields of the dual model. So this is the fundamental under USP4. So again, I use the notation. The first entry is the representation of USP4. The second entry is the number is the charge under this U1. And it has this specific superpotential. This is a translation of the original models, original superpotential. Aij is the dual image of this xi, xj. So in the Seiberg duality, Aij corresponds to this xi, xj, which was there in the Rodland model. So this first term is the translation of the Rodland superpotential, and the second term is the one which you need for the Seiberg duality. Okay, so this is the dual Rodland model. And in this model, the role of strong and weak is exchanged. The sign of zeta and the zeta dual are the same. So this is originally the weakly coupled phase in the Rodland, strongly coupled phase in the Rodland. But here it is opposite. Here it is weakly coupled with the help of superpotential, where the gauge group is completely broken. Here USP4 is completely unbroken. And the similar analysis tells you that the strongly coupled phase is again a nonlinear sigma model. So the rank condition on A appears, and the rank is 2. So A is Aij. So Aij spans 21-dimensional vector space. So this spans CP20, and rank 2 locus is a sub variety in CP20, and this spans G to 7 by this plays the role of Plücker coordinate. And there's this is additional hypersurfaces. So this is, in the end, it is the same as the original Calabi-Yau in Grassmannian. And in the weakly coupled phase, this is really easy. It's just solving the equations. And so this is the USP4 times U1 mod Z2 quotient of this space of P and X's. So actually, this equation completely determines X modulo gauge group. So this is represented by this P. And because X has rank the column 4, so this equation forces Aij to have this matrix have rank 4. So this is related to this Apathian variety. So this is a free quotient on this locus. So this is really easy analysis. Okay. And the Hosono-Takagi model, it's similar. O2 is replaced by SO4, and there's a similar equation, a similar matter representation, similar superpotential. This is the original superpotential for the Hosono-Takagi model. And the role of strong and weak are exchanged. In the Hosono-Takagi model, this side is weakly coupled, but here it is strongly coupled. SO4 is unbroken. Here it is it was strongly coupled, but this is completely classical, weakly coupled. Yes?
Can I check where the 15 comes from?
15. This 15. Sij is 5 times 5 symmetric matrix.
Yeah.
So 15. 5 times 6 over 2 is 15. Okay? Is that the answer? Okay. Sorry. I was too quick, perhaps. Yeah. Yes, and in the strongly coupled phase, the rank condition appears, and rank 2 locus. So S is related to Xij, and this is equivalent to isomorphic to the right congruence. And in the weakly coupled phase, in the dual model, it is quotient by this gauge group of this space, and this equation doesn't completely fix X tilde on the rank sorry, first of all, by this equation, rank of S has to be 4 or less because X has size 4. But for the rank on the rank strictly 4 locus, there are 2 solutions to X's for this equation. But rank 3 locus, there's a single solution, modulo the gauge equivalence. So this reproduces the ramified double cover. So this is completely classical analysis. Okay, so these correspondences have interesting mathematical consequences. So here there are mixed more than a half is mathematicians. So I'm going to talk about something related to mathematics. And so several consequences. One of them is that this Gromov-Witten invariance or FJRW invariance for the Landau-Ginzburg overfold, the 2 sides are related by analytic continuation. Another consequence is, so this is called so-called closed topological A model, and this is called open topological B model, and the category of B-branes are equivalent. And there can be more consequences. But today I'm going to focus on this B-branes, category of B-branes are equivalent. So in the case of Rudland model, so for each point of this space, there's a 2,2 QFT, then there's a category of B-branes. But for the nonlinear sigma models, this is known to be equivalent to some classical category called derived category of coherent sheaves. So in this side of this Grassmannian Calabi-Yau, on this side, Pfaffian Calabi-Yau. And if you draw a path from one phase to another, this determines equivalence of categories. For another path, you find another equivalence. And if you draw a loop, then you find autoequivalence of categories. So one natural question is to find what they are, what these functors are, using these gauge linear sigma models. So before talking about that, what's B-branes, the D-branes of B-type of B-type D-branes in gauge linear sigma model? So classically, it is the following. So let's consider gauge linear sigma model with gauge group V, matter representation V, superpotential W. A classical B-brane is specified by a G equivalent matrix factorization of the superpotential W. And it is denoted by M, Q. M is a Z2 graded vector space, which is a representation of the gauge group. And Q is a matrix factorization of the superpotential. So this is a function, polynomial function on the space of matter representations to the space of odd endomorphism of M. And this map has to be G equivariant. And also you need some additional data, grading, Z grading, compatible with Z2 grading. And they form a category, DG category. So this is the data to specify a classical B-brane. But in the quantum theory, maybe they may not define a well-behaved boundary condition, B-type D-branes. They may induce instability in the quantum theory, and that is the case especially when a continuous gauge symmetry remains unbroken. And their typical situation, continuous gauge symmetry remains unbroken, is around the phase boundaries, even for the original Witten's gauge linear sigma model. Near the phase boundary, the gauge symmetry, U1 gauge symmetry is unbroken. So this instability is important, can be serious near the phase boundary. And also inside the strongly coupled phases, like Rudland and Hosono-Takagi model, this is important. And also theories with simple gauge group typically has such a problem. And we would like to find a condition on this data to specify classical B-branes to define a well-behaved B-brane in the quantum theory. So that is the problem. And a proposal to find a criterion is to use something called hemisphere partition function. And I just write this expression for the hemisphere partition function. I don't want you to try to understand what they are. This is, what's important, it is given by some integral, contour integral of some integrand, of some meromorphic middle dimensional form. And so the condition, so this is specified anyway by the data of the theory itself, and also the data of the classical B-brane, is especially the Z2 graded representation part of the B-brane. And the condition is that this integration, the integral, is convergent for some gamma. So gamma has to be some deformation of the real locus, which avoids this meeting the pole of this gamma function. And I'm just going to show you the result of this convergence. So I do not go into the detail of this analysis of the convergence. But this is the main part of the work, physics work. So anyway, this imposes a severe constraint on representations of G that can enter into this vector space M. And for theories with abelian gauge groups, this reproduces something called grade restriction rule for d-brane transport across phase boundaries. And we shall continue to call this constraint grade restriction rule. And for example, let's consider a simple gauge theory with a specific class of matter representation, which is so-called symmetric. Namely, if you consider weight decomposition, then if you have a weight Q, then its negative is also a weight. So there's a pair between positive and negative weight. Or it may have a zero weight. So for such matter, the analysis of convergence is very easy. And the representation of highest weight lambda can be included into M when this inequality is satisfied. So there's some specific inequality determined by this representation, the weight for the representation. And for example, in the case of supersymmetric QC, namely the theory with gauge group USP2, USPK, with some n odd number of copies of fundamental representations, then irreducible representation of such USPK is specified by a Young diagram of height k/2 and the width ne. But this condition gives a constraint on the width. It has to be equal to or less than this number. And this is consistent with some so-called the 2D Seiberg duality, which are used, in which this k and n minus k minus 1 is exchanged. Okay, so this is an example of the grade restriction rule.
I have a question.
Yep.
So this defines some subcategory, right? So
That's right.
Is it still some? Does it have some nice property? Like is it still
That's right. That's right. Yes, thank you very much. So this is actually the category I showed you. So it's just a G equivalent category of matrix factorizations. So this is too huge. It's not a nice category. But if you restrict it to this, then you get a nice category. It's something called resolution of singular category. And this is actually the same. It turns out to be the same as so-called the non-commutative Crepant resolution found by two mathematicians, Spenko and Vandenberg. Yeah. So this is, yes, this restriction is important to find a very good category. Yeah. Yes, it reduces to a nice size category. It's like a compact, it's in terms of the geometric language, it's like category of compact space. And also smooth and compact space, sorry, yes. And sorry, no, smooth space, not compact. Yeah, but anyway, it is a nice category, nice property. Now I want to apply this to a Rudland model, Hosono-Takagi model, and their duals. And this is based on joint work with Richard Eger, Johanna Knapp, and Mauricio Romo. And these models have gauge group of the form H times U1 mod Z2. This plus 1H is identity, minus 1H is some order 2 element in the center of the group, and where H is symplectic or orthogonal group. And irreducible representation of the group of this type is labeled by this, Young diagram parenthesis I. So orthosymplectic group is specified by a Young diagram. For orthogonal group, you need to specify some additional plus or minus for some Young diagram. And also parenthesis I specifies the representation for the U1 subgroup of this, and it acts by the whole representation has a specific charge. Okay, now let's first talk about the grade restriction rule in the strongly coupled phase. So for the Rudland model, the strongly coupled phase in the Rudland model, only 3 series of representation is allowed. So this is like a width of the Young diagram. Only up to 2 is allowed. And the dual Rudland model, very interestingly, of course, zeta positive is strongly coupled, but zeta negative, I said it is weakly coupled, but for the weakly coupledness, you need a superpotential. If you forget about the superpotential condition, then there's an unbroken USP4 subgroup. There's a locus where there's an unbroken USP4 subgroup. So this is also strongly coupled if you forget about the superpotential. So for the dual Rudland model, for either side, you need this condition. So this is the width. Width 1 is the constraint. And for Hosono-Takagi model, it's similar. Width is bounded by 2, and the dual Hosono-Takagi model, which is bounded by 1. And this plus minus, so this is the Hosono-Takagi model has O2 subgroup, gauge group has O2 subgroup, and plus minus is this plus minus. So the identity is mapped to plus 1, and this entry, order 2 element in the outside the identity component is mapped to minus 1. For the plus representation, sorry. I'm sorry. Yeah, for C plus, it is mapped to identity. For C minus, this is mapped to this. So sorry, this is a bit strange way to write. So this is for C minus. C plus, everything is mapped to identity. And SO4 representation, this is like a 2 form of 4 vector. So it splits to self-dual or anti-self-dual 2 form. Okay, so this is the the grade restriction rule in the strongly coupled phases. So let's now talk about the grade restriction rule for B-brane transport from one phase to another. So let's start with the Rudland model. So this has, so if I theta parameter split, I said 3 singular points. But if you study the D-brane, if you consider boundary condition, if you consider 2-dimensional theory with boundary, for closed string theta was periodic by periodicity 2 pi, But if you have a boundary, it loses the periodicity, so it is unfolded to real line. So there's an infinite array of 3 arrays of singular points. And the path from one face to another is like this, and it can go anywhere between. So this is you have to go through some window through this phase boundary. So and then this grade restriction rule depends on through which window the path goes through. So for this specific window, this is minus 4 pi, minus 6 pi. So here there's minus 7 pi. So to the left of the minus 7 pi line, this is the allowed representations. 21 representations are allowed. If you choose another path, another set of representation is allowed. If you choose yet another set of representation is allowed, or a different one, another set of representation is allowed. And if you move this line to the left by 2 pi, then this set moves 1 step to the right. So that's the rule. Okay? So this is the result, and you can summarize the result in the language of categories. So for each homotopy class of paths, which I call window, W, between one face to another, such as this, let TW be the subcategory of equivalent matrix factorization made of the representations inside the box, so which I called grade restricted representations with respect to this window. And also, I denote by S the one at the strongly coupled face. These 3 series of representations. Then you have a diagram of categories. For us, for physicists, it's a diagram of RG flows. But you can also interpret it as a diagram of categories. Each arrow is a functor. And so this is the original classical B-brane category of the gauge linear sigma model. And in the Grassmannian phase, weakly coupled phase, it flows to the category of B-branes in the nonlinear sigma model, whose target space is this Calabi-Yau threefold inside the Grassmannian. In the opposite phase, the derived category recurrent sheaves, the category of B-branes in the nonlinear sigma model, whose target space is this Puffin variety. And these things are related, known to be equivalent to the derived category recurrent sheaves. And in the strongly coupled phase, there's a subcategory consisting of these 3 series of representations. And further, for each choice of window, there's a subcategory called TW of this, for which you can go safely from one phase to another. And it turns out that if you restrict this functor representing this RG flow to this subcategory, it turns out that these are equivalents of categories. And this diagram is actually the one found by Addington, Donovan, and Siegel. And this was actually very important breakthrough for us. So actually we aimed at reproducing this, and then found this by this convergence analysis. They found one such category, but we found 3 another such things, depending on this window. Okay. Now let's talk about the monodromy around singular point. So let's consider this particular, this particular monodromy. So let's consider the monodromy whose base point is in the weakly coupled Grassmannian phase. Go through this window and then go back through this window. So in the way to the negative phase, this box is good. On the way back, this another box is good. So this trivial representation, which was good on the way, is no longer good on the way back. But this is replaced by this C7, the charge 7 representation under this U1 factor. So in the language of categories, so you have two different subcategories, and you have equivalences, and so the monodromy can be regarded as going to this to this Pfaffian category through this subcategory, and then go back through the another subcategory. So this composition of functors gives you this autoequivalence. Sorry, maybe I used the different notation for the classical category. Okay, and so what you really have to do is to replace the C by C of 7. And there's a very convenient thing to realize this, and this is so-called the Koshio complex in this CP6. So this is, if you forget about the upper arrow, this is P is the coordinate of CP6, and this is so-called Koshio complex for on CP6, which is which is a zero object in CP6, and because related to the fact that this is zero object in CP6, it is so-called the empty brane. It reduces to nothing in the as a B-brane, and so this has C and C7, and you can bind these things. So if you find C component, you can bind this and cancel this C. Then you replace everything by this C by everything else, which is good in the way back. Okay. So this is the this replacement of C by C7 can be realized by this Koshio complex. For another monodromy, the change happens for a different representation. Again, fundamental to fundamental parenthesis 7. And then replacement can be realized by the tensor product of Koshio complex with this fundamental representation. And for the another monodromy, for the third point, the different representation should be replaced, and it is realized by Koshio complex tensored by this three-dimensional representation, symmetric power, second symmetric tensor representation. Okay, so this is K was empty in the Pfaffian phase, strongly coupled phase, but in this weakly coupled phase, in the Grassmannian phase, it is far from empty. It is something very important. K reduces to the structure sheaf of this Calabi-Yau threefold, and this reduces to rank 2 vector bundle, and this reduces to rank 3 vector bundle. And this binding process is realized by so-called the Seidel-Thomas twist. So the monodromy around 1, 2, 3 is realized by Seidel-Thomas twist by O, rank 2 vector bundle, rank 3 vector bundle. Okay, now let's talk about the dual model. And so dual Rodland model is useful when you want to know what is the monodromy whose base point is in the Pfaffian side. Okay, I'm going to show you the result of the grade restriction rule. So for this path, this set of representation is allowed. For another path, this, another path, this, another path, this. So again, if you move 2 pi to the left, then the representation is moving one step to the right. And for each so this can be written in terms of the diagram of either of RG flow or of categories. And so in the case of this dual model, both strong and weakly coupled phase, you have this non-trivial grade restriction rule. Anyway, for each window, you have a subcategory which turns out to be equivalent to the downstairs category. And for the monodromy, the replacement is necessary, and it's very similar to the original one. The thing is that the length of the Koshio complex becomes bigger for this. Yes, this is in CP21, so this is the length. The length 21 is the length of the Koshio complex. Anyway, so the one that's necessary, so this was empty in the strongly coupled phase, but in the weakly coupled phase, reduces to the structure sheaf or rank 4 vector bundle or rank 5 vector bundle. Okay. And so if you draw, so this tells you what the monodromy is for the loop whose base point is at the Pfaffian variety. So the monodromy around the point which is closest to the Pfaffian variety is always like by the structure sheaf. But for the other monodromy, it is given by not some higher rank vector bundle. And Hosono-Takagi model is similar. So for this path, this is the allowed representation. For another path, this, another path, this, another path, this, another path, this. And you have a similar diagram of categories. And this is actually also, which was found earlier by Jürgen Renamo. And the monodromy is given by Seiberg-Thomas twist. Once again, you do the replacement by Koshio complex. So what's interesting is that for the Hosono-Takagi model, one of the point has two objects. There's something called Coulomb branch, and there are actually two copies of Coulomb branch emanating from this, and associated with this, you have two objects, so-called vanishing cycle or vanishing brane. This O plus is the usual structure sheaf, O minus is the twisted structure sheaf. By the way, OS XS is obtained by, is a complete distance section of hypersurface of CP5 times CP5 modulo exchange. But this, before modulo exchange, you also have a smooth manifold. And this is actually a fundamental group Z2 by the exchange. And this O minus is the one which is non-trivial under this Z2. And for the other monodromy around the other point, this is the Seiberg-Thomas twist by a rank 2 vector bundle, which was before quotient CP1 times CP5 times CP5. It is CP4 times CP4. I'm sorry. CP4 times CP4. Yes. This direct sum of 1,0 and 0,1. And the other point is traceless symmetric second rank symmetric power of this, shifted by O of minus 1.
Kentaro?
Yep.
Those O plus and O minus,
yep.
Are they orthogonal?
Orthogonal? I don't know. I didn't check. I didn't know. Do you know?
No. And I'm wondering what
sorry, monodromy, sorry.
So around that loop,
Mm-hmm.
the monodromy would be twist by O plus and twist by O minus
Mm-hmm.
composed, I guess. Does that sound right?
Oh, sorry. Yeah. So what am I? Right. Sorry. Maybe I should have thought more carefully about. Yeah. So what I found is sorry. Yeah. Maybe this is something I haven't finished thinking carefully. Yes, there are two representations that has to be replaced. Right. Sorry, maybe I should have.
But I think it's okay if they are orthogonal, then you compose them and it doesn't matter which order you do it. So I think it's consistent.
Yeah, I haven't thought about it carefully. In the mirror side, there's this. Maybe it's something I haven't thought through. So, yeah, thank you very much for asking. It is something I should have thought more carefully. Yes, thank you. Yes, this is something I haven't finished thinking. We haven't finished thinking. Right. Yeah, thank you very much. I said there are two, yes, certainly there are two vanishing objects, but if you just consider loop, there should be a specific twist and, right, sorry. Sorry, this is something open, certainly, yes. Thank you. Yeah, you see similar things also for the dual model. Right, so the dual model, it's a bit more complicated, but it's similar. For each path, there's a good object. Okay, and then you have a equivalence of categories. And using this, you find this equivalence between these two, going through this. And once again, the monodromy, you see that there are two objects, but I haven't figured out what is really the monodromy using this. Yeah. Oh, yeah. Sorry. Yes, maybe. Yes. So sorry. Yes. It's not simple. I haven't even stated what the monodromy is. So if you yes, thank you very much. So if you okay, maybe I don't know. So maybe, for example, one concrete example. Yes. One particular case is C should be sorry. Yeah, maybe this is okay. This should be replaced by this, and this should be replaced by this. So if you find one entry in this, yeah, thank you, yes. If you find one entry in this, you should use the Koshuu complex for this representation. And if you find this entry, then you should use Koshuu complex for this. So you should use both of them for each appearance of this bad representation. So maybe it's the Seidel-Thomas twist by the sum of the two. Yeah. I think or not. Composition. Yeah. It's the right. Yeah.
Might be the same thing if they're orthogonal.
Yeah. Right. Yes.
It's the same thing if they're orthogonal.
Right. Okay, sorry, maybe I should have. So this, what's written here is certainly imprecise. Yes, you can consider the composition or the twist by the sum. Yeah. Okay, so maybe my time is over. So that's all.
Thank you for the nice talk. So, is there any question or comments?
You're talking about the mirror picture, or?
Sorry, mirror picture.
Okay.
On the other hand, the red concrete space, there are lens space vanished.
That's right.
So can we see the difference between the two in terms of Seiberg and
Sorry, difference.
So you are writing kernel, possible kernel for the
Mm-hmm.
Is there any difference between whether conical, simply conical or vanishing lens space? Is there any difference in terms of kernel?
Sorry, I think this so lens space has two local systems. These two are corresponding to this plus and minus. Yeah. So it should be mirrored. So this plus and minus should be mirrored to these two local systems on this lens space. Yeah.
Any question?
So in the last slide, so both of these two objects are used to Seiberg. These two, you have two objects.
Yes.
Are they spherical?
Sorry?
Are they spherical?
Spherical? I don't know. It should be, but I don't know. I haven't. No. I sorry.
So you said you expect them to be mirrored to local system like
That's right. Spherical meaning, it's this homology group is spherical. Yes, but I don't know in the.
Algebra is a homogeneous lens space.
Hmm?
So you say that it's mirrored to the lens space.
That's right. The lens space, the two local systems on the lens space. That's right. Yes.
So it's not spherical.
It is. What do you mean by spherical?
So X algebra is just C
Is it? So lens space, of course, because it has non-trivial H1, right? So if it is not H1 is not 0, you don't call it spherical.
So this you cannot construct equivalence.
We cannot construct an equivalence. Oh, is that so? Then that's a mystery.
I think it should be spherical by looking at the window. I mean, when you draw the window,
Yes.
you know you have no backward morphisms in the window. So most of the causal complex gives nothing, and I hope each object is spherical.
So there are two different opinions, which is correct.
You can detect it from the monodromy matrix. If we compute the monodromy matrix,
Yes.
you can detect if it's spherical or not.
The monodromy matrix is just for the whole things, not the individual things.
No,
Yeah, yeah, yeah.
You can check if it's a product of it.
But we don't know how to compute the monodromy matrix for the individual twist. Yeah. We only have the one for the full loop. Yeah.
Any other question or comment? If not, let's thank the speaker again.